Welcome to the Explainer. Today, we're setting out on a massive planetary scale investigation. We're going to learn exactly how scientists read the Earth's history like this giant, incredibly complex puzzle. Because you see, every mountain, every coastline, and literally every grain of deep sea sediment holds a clue to the deep past. But how do we actually decode it? I mean, how do we look at a riverbed or study the vast distribution of our continents and oceans and extract thousands of years of climatic data from that? Well, we're going to unpack the science of geomorphology today, tracing its evolution from, simple observation all the way to hardcore quantitative analysis. Okay, let's dive into this. Before we get to the advanced equations and the deep sea drilling, I want to ground our investigation with this really famous thought from Isaac Newton. It just perfectly captures that profound sense of human wonder we've all felt when looking out at the physical world. For centuries, our study of the Earth was driven purely by this kind of awe. Like a boy playing on the seashore, picking up a smoother pebble or a prettier shell, looking out at the vast distribution of continents and oceans, and just wondering, why exactly are the land masses shaped this way, and how do they interact with the sea? So, to answer that, here is our macro to micro agenda for today. First, viewing the Earth system. Second, the quantitative revolution. Third, measuring the landscape. Fourth, clues in the coastlines. And finally, unlocking Earth's past. Section 1. Viewing the Earth system. To truly grasp how far the science of geomorphology has actually come, we kind of have to look at where it started, with the raw, awe-inspiring realization that our planet is this incredible subject that just demands to be understood. Consider this quote from astronaut Edgar Mitchell. He said, "My view of our planet was a glimpse of divinity." When the crew of Apollo 17 traveled between the Earth and the Moon, they photographed the stark, beautiful contrast between the deep blue of the oceans and the orange-red deserts of continents like Africa. That visual distribution of land and water, it's just mesmerizing. And historically, early geography was rooted right here, in this broad descriptive awe. It was essentially looking at the Earth simply as the home of humankind. In fact, the word geography literally translates to Earth description. So for a long time, the whole discipline just focused on observing the physical environment, studying its spatial organization, and looking at interactions with human society. It was a highly qualitative discipline. You made a map, you described the shape of a valley, you jotted down what the shoreline looked like. But eventually, this purely descriptive approach sort of hit a wall. Scientists realized that just describing a landscape didn't actually explain the hidden underlying laws that governed how it was formed in the first place. Section 2. The quantitative revolution. Now, what's really interesting about this slide is the stark contrast between the old world and the new. That realization we just talked about triggered a massive paradigm shift in the middle of the 20th century. It changed the discipline entirely, taking it from simple map-making and subjective description straight into rigorous, hard science. We move from the old qualitative approach, subjective interpretation and basic observation, to a total quantitative revolution. This was driven by a philosophy called positivism, which basically demanded that geographers become neutral observers, searching for actual hard spatial laws. It meant description had to be replaced by precise measurement, using systems theory to understand exactly how the physical world operates. This shift brought about a systems representation of model construction. Instead of just looking at a mountain's shape and saying, "Oh, that's pretty," landforms began to be seen as balanced, dynamic systems. Physical laws, process noise, and measurements all feed into structural and measurement knowledge now. That old preoccupation with just simple, progressive landscape development, totally gone. In its place came this powerful understanding that physical process and physical form are intensely mathematically interrelated. Basically, if you know the inputs, you can absolutely model the outputs. Section 3. Measuring the landscape. But how do you actually measure those inputs and outputs out in the real world? Like, how do you quantify an entire mountain range or a vast desert? Well, the foundational tool scientists invented to execute this math is called morphometry. It's the rigorous measurement of landforms to generate data relating physical form directly to environmental processes. And this is absolutely crucial. Having objective numerical data allows scientists to actually test their theories. By assigning interval and ratio scale data to a landscape, we can exploit the relationship between form and process in both directions. We can interpret how landscape adjusted to past environments, or, flip it around, look at a current landform and predict the exact environmental processes that created it. And this brilliantly illustrates how that plays out in the field. Look at the quantitative geomorphological indicators here. If a geomorphologist finds pingos, which are essentially these giant ice-cored mounds of Earth, they aren't just looking at weird bumps in the ground. No, they're looking at hard data indicating the historical presence of permafrost and negative mean annual temperatures. Or, if they measure fossil dunes in a continental interior, they can calculate former wind directions and precipitation levels. The landscape itself is literally like a giant hard drive, quietly recording ancient weather data. Section 4. Clues in the coastlines. While continental interiors are super fascinating, if we really want to see the relationship between form and process happening in real time, we need to look at the edges. Coastlines are an absolute dream for geomorphologists. Why? Well, the coastal zone features incredibly high energy inputs from waves and tides. Think about it. In a typical landscape, it might take thousands of years to see a mountain erode. But on a beach, the sheer force of water pushing sand ashore and gravity dragging it back down, combined with sudden violent storms, promotes incredibly rapid changes. The beach is constantly seeking an equilibrium slope, where the sand moved onshore perfectly balances the sand pulled offshore. And we can measure these changes in days or sometimes even hours. But coastlines also record massive long-term changes. Take a look at this detailed geomorphological mapping of Nielv up in northern Norway. We're looking at raised shorelines. Shorelines represent the exact interface of land and water at a specific point in time, right? So by mapping displaced features, like the marine limit, which is the absolute highest level the sea reached after glaciers melted, scientists can track how the exact distribution of our continents and oceans physically shifted over time. When the ice melted, the oceans literally filled up with extra water. But at the same time, the Earth's continental crust, finally freed from millions of tons of heavy ice, bounced upward. These mapped shorelines are the physical receipts of those massive planetary movements, leaving ancient beaches stranded high above the current water level. It's wild to think about. Section 5. Unlocking Earth's Past. So we've measured the dunes and we've mapped the changing shores. But to truly decode the Earth's deepest history, we have to transition from the macro landscape down to the absolute microscopic level. To do this, we use the oxygen isotopic analysis equation. This is arguably the most profound tool geomorphologists use to read deep time. Scientists extract deep-sea sediment cores right from the ocean floor. Inside that muck are the tiny fossilized calcite shells of microscopic marine organisms called foraminifera. By measuring the ratio of stable oxygen 18 to oxygen 16 inside these microscopic shells, using this exact formula, scientists can determine the isotopic composition of the seawater at the exact moment that tiny creature was alive thousands of years ago. And when you run that equation on thousands of samples, all the way down a deep-sea core, you get this, a master curve. Notice the distinct cyclical variations as you go deeper. Those aren't just random squiggles. You see, glacial ice is isotopically lighter than seawater. So when ice caps grow during an ice age, they lock up the lighter oxygen, leaving the ocean enriched in heavier oxygen 18. This curve is literally tracking the expansion and contraction of continental ice volume over time. It's a continuous visual record of the Earth's glacial and interglacial stages. And the scale of this record, it is just staggering. 1 million. By dating these deep-sea cores using magnetic stratigraphy, scientists have been able to trace this continuous, highly detailed record of climate fluctuations back over 1 million years. Long before humans ever walked the Earth, the oceans were silently archiving the exact global temperature and ice volume year after year right inside the shells of microscopic plankton. It really brings us full circle, doesn't it? From the qualitative awe of looking at our blue planet from space to the precise quantitative measurement of oxygen isotopes deep beneath the seafloor. We've seen how every system, from a coastal beach to a continental fossil dune, acts as a perfectly balanced ledger of environmental process and form. Which leaves us with one final, incredibly provocative question to think about. If the Earth's landscape so accurately and permanently records its past, what is it currently recording about us? Thank you so much for joining me on this explainer. Keep wondering, keep observing, and I'll catch you next time.